Now here's an example where we have a variable a, and it does make sense to look at multiple locations. So I'm setting p equals to a. So here you see I'm using array notation, I'm using pointer notation, and I can treat these a and p as about the same thing. Right? I can look at the 0th item of a, I can look at the first item that p points to, that first being the one after the 0th, or I can add 2 to p and look there. All three of these ways of accessing the memory are going to produce the same kind of result. So that should show us 1, 2, 3. Let's make sure of that. Right, 1, 2, 3. And again, that's because a is an array of 3 integers. And we look at the 0th item, which is 1. Or p equals the address where a lives, and if we look at the integer at index 1 there, that's 2. Or if we take that address, add 2 to it, then we used to be pointing here, now we're pointing here, and we look inside there, then we'll see a 3. So the memory view of this is that a, the array, lives somewhere in memory, p has the address of that array, and it sees inside there. You may wonder why we don't use an ampersand on a. It turns out you can use an ampersand or not use an ampersand. It's like functions. When you have an array, there's implicitly an ampersand in front whenever you use the variable name. So in this case, p and q are going to be the same thing. Right? So when we print both of those out, we'll see the same address. But if I take the address of p, that doesn't mean the address of a, that means the address of the variable p. Right? So it's going to be something different. That is, p and q will both point to the same a, but the address of p, that will be different than the value of p. Right? So let's try this just to check it as usual. Um, and we see that the two numbers are the same, and that number is also the same. This warning is warning us that we don't seem to be matching up our types here, even though the representations turn out to be appropriate.